Hello, calculus fans. So back in Calculus 1, we talked about definite integrals. These are for functions of a single variable. Let's recap how we did that. Let's suppose that we have a function that's defined between a and b. We take the interval from a to b, divide it into n subintervals of equal width. The width of each subinterval is delta x, which is b minus a over n. Then we choose sample points in each subinterval. It doesn't matter how we choose those sample points. Then we form this Riemann sum, and then we define the definite integral to be the limit of those Riemann sums. This is, of course, assuming that the limit exists. In the special case where the function is non-negative, then we can interpret the Riemann sum as approximating the area under the curve. We'll show this in a picture in a moment. So the integral from a to b of f of x dx represents the area under the curve from a to b. Here's a picture of the curve and the approximating rectangles. You'll notice that the approximating rectangles are created by finding the height of the curve at the sample point and using that as the height of the rectangle. We're now going to do the same thing for functions of two variables, and it's going to be a somewhat similar process. So we have a function of two variables that's defined on a closed rectangle. So that's AB cross CD. So the x values are going between a and b, the y values are going between c and d. So this is all in two-dimensional space now. And we'll suppose, just for now, that f of xy is non-negative. That way we can have a geometrical interpretation of what we're working on. So the graph of f is a surface whose equation is z equals f of xy. Let's let S be the solid that lies above R and under the graph of f. So it's the set of points in three-dimensional space where the z values go between 0 and f of xy, and the xy is in the rectangle. This is a picture of what we are intending here. We have some surface that lies above a rectangle, and we're going to try to compute the volume that's under the surface and above the rectangle. So our goal is to find the volume of S. Alright, so as a first step, in much the same way as we did in Calculus 1, we're going to divide the rectangle R into sub-rectangles. In Calculus 1, we divided an interval into sub-intervals. Here we're dividing a rectangle into sub-rectangles. We'll accomplish this by dividing the interval from a to b into sub-intervals, and we divide the interval from c to d also into sub-intervals. And then we'll draw lines parallel to the coordinate axes through the endpoints of these sub-intervals, and what that does is creates a grid of sub-rectangles. Each has area delta A, which is delta x times delta y. Let's look at a picture. This picture shows the rectangle along with all the sub-rectangles. Now we go one step further and also show the sample points that we're going to be choosing in each sub-rectangle. It won't matter which sample point we choose in each sub-rectangle, since ultimately we're going to be thinking about taking a limit. So we choose a sample point, xjk star, yjk star, in each rectangle. Then we can approximate the portion of S that lies above each rectangular box. We'll think of this like a column. It has base rjk and height f of xjk star, yjk star. The volume of this box is the height of the box times the area of the base rectangle. So if we add all these up, then we get the volume is a sum of all of these columns. Let's look at a picture. This picture here shows you the volume of one column. you have to imagine that there's a whole bunch of these. This is one column over one subrectangle, and then there's a bunch of these columns. The top is flat because we're making this into a tall, thin, rectangular box. So the double sum means that for every rectangle, we evaluate f at the chosen sample point, and then we multiply by the area of the rectangle, and we add up the results. We believe that this approximation to the actual area under the curve will get better as m and n get larger, and we're going to expect that the volume will actually be the limit of this double sum. So we're going to use this expression to define the volume of the solid that lies under the graph of f and above the rectangle R. So the limits of this type occur a lot, not just in finding volumes. And we're going to see a lot of these other applications later. And even when f is not a positive function, this definition still makes sense. It may not make sense in terms of trying to compute a volume, but it can give us a different sort of interpretation. So we'll make the following definition. We're going to say that the double integral of f over the rectangle R is this guy here, the limit as m and n approach infinity of the double sum of the areas of each rectangular column, provided this limit exists. And we're going to say that a function is called integrable if this limit exists. One of the things you do in advanced calculus is you prove that all continuous functions are integrable. Now, even discontinuous functions can be integrable as long as they're not too discontinuous. So if f of xy is bigger than or equal to 0, then the volume of the solid that lies above the rectangle and below the surface is this double integral. And the sum without the limit, this sum that's in the definition of the double integral is called the double Riemann sum, and can be used as an approximation to the value of the double integral. And if f happens to be a positive function, then the double Riemann sum represents the sum of the volumes of columns, and it approximates the volume under the graph of f and above the rectangle. Now at this point, we don't have a way of computing these integrals. In Calculus 1, what we did was we developed the fundamental theorem of calculus. And later on, we're going to show how that can be adapted to be able to compute double integrals. Okay, that's all for now.